So thank you very much for the opportunity to talk at this conference. And today I would like to present some interesting observations and pitfalls of model evaluation. First of all, just try to think about when I say that my forecast is better than your forecast. What do you think I did? Yeah? So might be you think I calculated one metric with your forecast and my forecast. Might be I calculated the set of metrics. Might be I clustered my data in different subsets, different categories, and calculated metrics on these categories. Might be I calculate return of investment on different forecasts. So I might be these different things, but what is important, do you really know if this methodology leads to selecting better forecast? We used to do repetitive things or the same in the same way based on maybe our experience, maybe based on our experience, other experience, or maybe based on some just workflows that everybody does. Yeah? So let's try to a bit rethink what we do and actually what's the effect of this and what actually biases it can lead to. So first of all, let's look a bit of the history of forecast evaluation and what is traditionally done. First of all, traditional forecast is quite often quite simple statistical algorithms, some moving average, versus modern machine learning forecast is complex machine learning algorithms, okay, obvious. Also, traditional forecasting was mostly done for some univariate time series where you just use your time series and do some forecasting, while modern forecasting is usually using multiple influencing variables, effects. For example, for demand forecasting, it will be weather, prices, cannibalization, a lot of stuff. So on top of this, we have that traditional forecasting was forecasting on quite aggregated level, because if you use time series, you need really a lot of kind of data to run a simple algorithm on quite aggregated level to pick up, for example, seasonality or whatever. Yeah. While machine learning forecasting can go quite to very granular prediction level and predicting product demands on really product location, hour level, and so on. So now taking this in mind, what's actually evaluating traditional forecast? Yeah? Quite often it's one, maybe two metrics. In sales, forecasting is actually often mean absolute percentage error, according to not so old studies. So also quite often what we mean that there are some arbitrary benchmarks that, okay, we have industrial benchmark of 70% accuracy. Then I ask like, okay, why 70% accuracy? Because everybody uses 70% accuracy. I mean, that was the answer. That happens. Yeah? Also quite often, what we observe is that comparing metrics between different subsets of data, like this approach is used to identify forecast problems. Yeah? But can we really use the same things for machine learning forecasting on a really granular level with multiple influencing factors? Let's discuss and look a bit further. Then let me introduce also our demand forecasting use case. So demand forecasting use case that we are mostly doing at Blue Yonder for predicting demand for retail and manufacturers has like few important features. First of all, demand is a random variable. So it doesn't matter how precise we can predict demand for tomorrow. Anyway, it has some statistical fluctuations. Then demand is often discrete quantity on countable atomic objects. Would it be apples, T-shirts, MacBooks, whatever. And underlying processes are rather independent in time. And for example, one customer coming to the shop is independent to another customer coming to the shop. And it can come or cannot to come. That's why, for example, some underlying assumptions as Poisson distribution for demand can make sense. Demand can be demand as sales, for example, for grocery, fashion, and typical granularity of forecasting will be product, store, date. Also, it could be for manufacturing, like demand as an order. Then it could be consumer packaged goods, and typical prediction granularity could be that we predict for product, location, for example, distribution center or manufacturing, and for example, week or even months, and maybe customer channel who is buying from the manufacturing. And traditional, of course, evaluation process is that we train on something in sample, and we predict something for out of sample, obvious, and then we compare our metrics out of sample. A few more words that for traditional forecasting, with relatively simple algorithms, we like split in trend, seasonality, and etc. While machine learning forecasting can give us much more advanced forecast by using additional causals like weather, promotions, prices. Like here on the right example, you can see effect of promotions. And definitely, if you would not include promotions, they can't be learned because then like might be independent from seasonality or other time series patterns. One more important thing is that modern machine learning forecasting quite often is probabilistic forecasting, because it's quite different things if I say that tomorrow we will sell 15 apples from tomorrow we will sell 15 apples on average, and there is your probability distribution. That we sell, for example, 22 apples with 2% probability, and so on and so on. There are a number of benefits that we can better control of our uncertainty, and we can do smarter objective optimization. I will tell a few words on the next slide. And for number of the next examples, we would assume that demand has a Poisson distribution that is kind of reasonable for retail business where we're selling apples, t-shirts, or whatever. Then let me go further, and I think the last introduction slide is that like what actually the main usage of such forecasting. It could be price optimization, it could be stock fulfillment or storage replenishment. It could be promotion planning, manufacturing planning, a lot of stuff. And what actually benefits? With deterministic forecast, we predict 15, we might be order 15, maybe with some safety gap, who knows, yes? With probabilistic forecast, we can do much clever optimization of some particular cost function, or for example, we can minimize combination of wastes and loss because of the lost sales costs, depending on our target function. Also limitations. For example, we have only 10 in stock and we predict 15, okay, then we can correct our predictions and go with final prediction of 10 because we can't sell more than we have in stock. Yeah. But in limitations, when we're talking about probabilistic forecast, we can just cut away part of the probabilistic distribution, and then we again have nice probability distribution we can work on and optimize on. So having all this in mind, background, and our use case, let's go directly and and look at our first problem about metrics selection. The main idea of evaluating forecast is for when we're talking about single-valued forecast, is just we take prediction, take observation, calculate metric. For example, relative mean error. Done. Yeah. When we're talking about probabilistic forecasting, there can be two approaches. Either we take the full probability distribution, compare with observed distribution of our sales, and we can calculate different statistical distances between these two shapes and these two distributions. There are a few problems with this because, first of all, if we do this, we can't really compare with deterministic forecast, and as well, it's a bit hard to derive business value from this and explain to business people, not statisticians people, actually what we did and why it makes sense. And and so on. Alternative way is that we have our prediction probability distribution, and then we take some point estimator from this predicted probability distribution, for example, mean. Yeah? Then we also have our observation, and then we calculate some particular metric. And then the other problems arises is the different point estimator selection can lead actually to drastically different results. One thing if I select mean of my distribution, another thing if I select, for example, median. And actually a lot of metrics don't make sense for some particular use cases. As it was discussed before, like mapper for something with zero sales situations. And then we will go with this compare numbers approach for first examples. Let me just show you some formulas and have a look at two examples. Imagine we have two examples, one product that is sold on average with 9.47 sales per day, and another product that is sold 0.6 sales per day. What will be probability distribution under Poisson assumption you can see on this slide. As well, you can see mean, median, and so-called -1 median that we'll explain further for this particular distribution. And let's assume that we ideally predicted this distribution and everything fine. Yeah? Then the question arises, actually, what will be the ultimate number of our metric, and assuming that we ideally predicted this distribution, but it's just taking this statistical nature. Yeah? If we look at mean square error, actually the mean square error is minimized by mean of this distribution. And the mean of this distribution for the left one is 9.47, and for the right one is 0.6. Yeah? Okay, so we will take this mean, incorporate in mean square error, and then we get the best mean square error. Yeah? If we're talking about mean absolute error, actually it's minimized by median. So it will be 9 sales for left, and actually 0 sales for right case, for slow selling case. And if we're talking about mapper, the smallest mapper is achieved with -1 median. It is median of modified distribution, as you can see here. And actually, the numbers that will minimize a mapper will be 8 for relatively fast-selling products and 1 for relatively slow-selling product on the right example. So you can see that actually different point estimators gave us really different values for metrics, and actually they optimize even different metrics at the end. So it means that if you would have two forecasts that you optimize, or that you like created in some way, it might be that using some particular metric will give you wrong result just because you created your forecast based on minimization of one function and then you compare another function. And what you can do, you can select smart point estimator for this case, depending on the metric you want to evaluate your model with. So yeah, select metrics wisely and select metrics that are relevant for your business point estimator, or vice versa. If you know that your focus will be evaluated on under some metric, you can find out what the point estimator is minimizing these metrics, and then take this point estimator from your probabilistic forecast. Now moving to a bit more general problem is like apple-to-apple comparison. That actually not so easy sometimes and not actually so widely understood. Also called scaling problem. Let me give you a number of toy examples. For example, we have one product with the following demand that it either with 50% probability it has 0 sales, and with 50% probability it has 1 sale. Yeah. And then per day it was sold either 1 or 0 times. So what will be the best demand prediction? It will be obviously 0.5. Yeah. And 0.5 will lead to RMAE of 100% for perfect forecast. Then if we just aggregate it in time, just one bucket in 2, we will get best demand prediction of 1. And then we get RMAE of 50%, actually. So formally, we took the same forecast, we just did aggregation, and we got drastically different errors. And if you go and say like we have 100% error or we have 50% error, or sometimes customers has, or your boss or your organization has some old forecast on quite aggregated level, they calculate some metrics, then you bring some advanced granular forecast, and then they calculate the same metrics, and sometimes even forgetting aggregating your forecast to the corresponding time level or the corresponding granularity. And then it can lead to the problems. You should understand this at the end. And let's take another example for something high-selling product that either sold 10 times or 20 times. So actually, with bad forecast of 10, while the best forecast will be 15 sales per day, we'll get RMAE of 33%. That actually better than previous examples. So at the end, if you're evaluating on really, really different scales, different forecasts, and you don't make your scale consistent between different forecasts, or you can end up on this pitfall of scaling issues. Yeah, so what kind of conclusions we can derive from this? First of all, we need to compare metrics for different forecasts at the same aggregation level. We shouldn't compare forecast for apples with forecast for boxes of apples. We should compare apples to apples. Then we should understand that when we compare benchmarks, we should know where these benchmarks come from what granularity, from whatever. Yeah? So we shouldn't just accept that there is some benchmark for our forecast quality. And when we're comparing different data subgroups, for example, Apple sales apple with dragon fruits, we should understand that actually they have different selling rate and they have different statistical nature for this product. That's why some metrics that make sense for Apple, some errors that make sense for apples will not make sense for dragon fruits. Second problem is knowing your limits. So if your boss comes to you and asks you okay, I want tomorrow you to provide forecast with 95% accuracy. And it's like, what? Yeah. Why 95% accuracy? Why? Even can we reach it? I mean, what you do? Do you do prototyping or whatever? So it's better to understand first actually what the ultimate error you can reach. Yeah? Because your error has two ingredients. First of all, is a reducible error that, for example, overall forecast bias that can reduce, and irreducible error, for example, statistical fluctuations or statistical nature of your data. And if we take two previous examples, for the first example, actually best relative mean absolute error is 0.17. So 70% error that we cannot go down further. And for second example, the best relative mean absolute error will be 24%. So we really can't go down below this error. And again, if your boss asks you, can you please reach 95% accuracy? Then you can say, okay, we have average sales of 9.47, and taking into account statistical nature, actually we just cannot reach this accuracy as we cannot exceed speed of light. It's just statistical nature. We can't reach it. We can't do better than, for example, 0.24. That's why it's important before evaluating forecast to understand what is the ultimate performance you can reach based on some reducible error, for example, based on statistical fluctuations. And this actually, it will highly really depend on scale you're working on or your predicted demand scale. Yep, so because you will have different statistical uncertainty based on your predicted demand. So, what was wrong? Yeah. Then next problem I would like to talk about is grouping your data in the correct way. It is important to, quite often it's important to evaluate, when you're evaluating models, that you actually group your model, for example, between slow-selling products and fast-selling products. Yeah? And now you both come to you and ask, like, actually, why your forecast is so bad for slow-selling products in comparison with good selling products? Or why some particular forecast actually better for slow-selling products than yours forecast? And then you start thinking, and okay, and that maybe our methodology is not fully correct. And here you can see as an example that to example, imagine you have demand with either 90% probability to stay the same and 10% probability to change. And you have just two states, 0 and 1. So either 0 sale, either 1 sale. So good forecast for the first case will be 0.9, and for the second case will be 0.1, while bias forecast will be 0.85 and 0.05. And at the end, if you actually bin your final results in observed demand, you will end up having your actually blue, so reasonable forecast, looking like worse than actually biased forecast, just because you binned with some information that you will get for this future information that you will get later and not now. And that could be a big, big problem in this case when you're really evaluating forecast for different subgroup of data. And what is called kind of Heinzen bias, and you can go and look at this blog post for more details. And generally, here you can see on the left and right mean predicted demand on the left with binned observed demand for Poisson numerical experiment under Poisson assumption. And you can see that it's actually, even for ideal forecast, it will lie far from diagonal. So the conclusion on this is that better to do your demand splitting or subgroup splitting based on information available now. It will maybe product groups, it may be predicted rates, like being predicted demand, but not on something that we'll get in the future, like real observations based on the future. Otherwise, your judgment could be biased based on this. And in addition, actually, binning demand makes different product really more comparable. And now, coming to my conclusion, let's take everything together and try to understand actually how we can avoid all these biases. First of all, on the left, we select some meaningful metric. For example, for us, it would be relative mean absolute error. Secondary, we knowing our limits. So we know that our limits, we cannot exceed and get smaller error that under this red curve. Then we also bin or group by our current available data, for example, bin predicted demand. And as well, actually, when we bin and predicted demand, it makes different product groups or categories, like apples and dragon fruits, more comparable. Yeah? And here you can see blue and green focus 1 for product type 1 and 2, and yellow and red focus 2 for product type 1 and product type 2. And actually, this picture is kind of amazing because you can extract so much information. Let me give you a few examples. You can already judge that actually forecast 1 is worse than forecast 2 because your metrics are much below for all sailing rates. And even you can see that a lot of opportunities for improving your forecast with forecast 2 you get from high selling products with around sailing rates of 1,000 and 200. Second interesting observation that, for example, for product type 1 and product type 2 are not really comparable. You can see that product type 2 doesn't have high selling examples. It's mostly only within South Atlantic region with small demand. But actually, it is much closer to ideal situation. And in this case, if you would just aggregate everything, you will get worse metric. But from this, you can judge it's much closer to ideal case. And also, you can judge that focus 2 can't improve this metric much. You can't improve it much because it's already close to ideal, close to its statistical limits. Yeah. So, and that's more or less it what I wanted to tell you and show this picture. So, yeah, think about this, think how you evaluate your forecast, understand your limits, do smart grouping, and let me know if you're interested in some more information. And yeah, don't hesitate, join our webpage and our blog post. We are posting more information about and more details and more math behind all these problems that I described today. Yeah, thank you.
Thank you a lot, Ilya, for the insights today. Let's go to Slido. So the first question, you talk about picking the right metric for different scenarios. Assuming your customer doesn't understand much, isn't the answer always MIPA or MIA?
If the customer doesn't understand much, I mean, if the customer doesn't understand much, first you need to try to educate customer. You shouldn't give up on educating customers. Second point is you should understand what actually is important business case for the customer and try to select metric that correspond to the business case of the customer, because usually metric is illustration of losses that customer will experience under some assumptions. For example, it could be like lost sales or whatever. And different metrics are actually, since they're minimizing different numbers, can be more appropriate for some particular type of loss that is important for customer. So I hope it answers this question.
Thank you. Next one. You mentioned you can compare the predicted distribution and the actual one. How do you get the actual distribution since you just observe one sale number?
I mean, we have quite long evaluation period. For example, I'm not talking about that we observe exactly one, but we observe sales over a long period of time, and we run evaluation on backtest on a long period of time, and then we'll already have some distribution of sales at the end. Of course, on one number, you cannot do much statistical difference between different distributions, but if you collect enough backtest data, then yeah, you can.
Cool. Demand tends to be over-dispersed. Is Poisson distribution really better than negative binomial distribution, for instance?
Negative binomial is definitely better, but it has two parameters, so it's a bit more complex, but it's definitely much more appropriate for this use case. I just use as Poisson assumptions as a simpler assumptions because it has only one parameter.
Cool. For discrete sales forecast, should we not first discretize or round the forecast before we calculate the error?
I think rounding should be on the part of decision making, how this forecast is consumed at the end. Because what we would like to provide, the best forecast is possible. Because if we, when we provide the full distribution, at the end we provide this full distribution, and then this distribution can be optimized. And distribution formula is collection of, again, rounded numbers with their probabilities. So at the end, it always comes from how this forecast will be consumed and how this will be forecast used at the end in some further optimization process or ordering process.
So we are running out of time, 1 minute, so it has to be a short answer, this one.
Okay.
When predicting a distribution, isn't the mode or peak of the distribution the best point estimator?
Depends on the business case and the metric. Again, as it was exactly the messaging that different metrics or different business cases could lead to different point estimators of your distribution as the most optimal point estimators.
Thank you. So we have 3 leftover questions, which you might direct directly to the speaker, as we are out of time. But please join me in to thank you, Ilya, for the great presentation.